In this video I'm going to talk about some emergent decoupling technologies, emergent decoupling capacitor technologies. And by this I mean getting away from the traditional surface mount components, although those are going to be included in this list. First up, we have organic semiconductor, or OSCON, electrolytic capacitors. And this is a way people have found to pack a lot of capacitance into a small volume. Remember that electrolytic capacitors have the highest capacitance per unit volume of any type of capacitor out there. And these have high C, high capacitance, and low ESR, equivalent series resistance. If you're looking for a big beefy capacitor, this might be something you want to consider. Next we have one thing I like is a wider surface mount technology package. And traditionally capacitors have been, or surface mount components have been twice as long as they are wide. So if you had something that was labeled as 06, 03, or 08, 05, or 1210, what this means is that this one is 80 mils long and 50 mils wide. Now you can buy capacitors that are exactly the opposite, so they're like 05, 08, so they're 50 mils long and 80 mils wide, whereas before they would look like this. Now they would tend to look like this. Okay, and what this does is it decreases the inductance. There's a larger, it decreases the resistance, decreases the inductance, and the wider package gives maybe up to about a 40% reduction in ESL. So 40% decrease in ESL, which means you can use these capacitors at up to higher and higher frequencies than these traditional long varieties. Next we have the interdigitated capacitors, or IDC, or low impedance capacitors, LICA. And these work by having interdigitated fingers, I guess, where current is flowing in opposite directions. So they tend to, the way they're structured, and I don't fully understand it, but current tends to flow in opposite directions while it's in the capacitor. And because it's flowing, it's in opposite direction, you have a smaller magnetic field and a lower ESL, lower equivalent series inductance. Next, we have changes in the way printed circuit boards are manufactured, and this is actually, I think, an important emerging trend. And this is called something like power plane capacitors, buried capacitance, integrated capacitance. It all refers to basically the same thing, and it comes down to two things. One, smaller distances between layers, and two, higher dielectric material, higher K material. And let me draw what I mean. Let's say in the traditional case you'd have a metal layer here and a metal layer here, and in between we have some sort of dielectric. Now this is the distance, and this is the dielectric constant of the material in between. And since for a parallel plate capacitor, the capacitance equals the dielectric constant times the area over the distance, if we can either increase the dielectric constant or decrease the distance, we increase the capacitance and the decoupling between, say, if this was at plus 5 volts and this was at ground. So what you do then is you'd have a system that looks like this, where it has a different distance, a shorter distance, and a different kind of material between the metal layers. Next, we have the trend that some manufacturers are starting, or maybe it's not just starting, but they're including decoupling capacitors in the integrated circuit packages themselves. So you have to worry less and less. Well, you don't have to worry less, but it's an added margin for error in your circuit, and that's an interesting idea, and one that I like. Next, we have dissipative termination, and this means at the edges of your printed circuit board you might include a very high resistance between the power plane and ground. So as you draw it out, like over here, I'm drawing it outside the printed circuit board, something like that. There's the ground, this is not very well drawn. But the idea is that if you had electromagnetic energy coming down the plane, when it hits the end, there's a boundary condition there where basically it's not going to be able to propagate that energy back into the system, and it just goes to essentially a zero at the border. Last, we have layout changes. And here we have a couple major things. One is that you may put the capacitor underneath the integrated circuit to lower the inductance. So if you had a distance between the front and the back side of your printed circuit board and you had an integrated circuit here, you may include a via right there and a via here to come down and then put your capacitance, the capacitor right there. So it's very close. It's not off on the side like this. And depending on the structure of the printed circuit board, that may be exceptionally close to the integrated circuit. And in keeping with that, you would want to, as I mentioned before, put the vias within the pad of the capacitor to really cut down on the loop inductance, the length between this capacitor and the power and ground plane that it's supposed to decouple.